if you recall the definition for the model state space that we spoke about earlier, is simply the set of all possible configurations of your system according to the typing constraint for the constants and also variables, and also subject to any extra properties that you may declare as invariants. That's basically what a model state space is. That's something you would like to review in an earlier slide before you move on. And for the state space for the model, not just for the initial one, but for all the later ones, we always talk about two different parts. One is called a static part, the other one is called a dynamic part. And for those of you who already completed lab number 1, you will know that if we actually want to type in this model into Rodin, the static part will be the context, and the dynamic part will be the machine. Right? That's something you want to make sure you also understand how to put it into practice. Right, let's now talk about, let me go over the slide, go over all the points, and then I'll summarize and annotate with some additional points on the iPad. That'll be the plan. The static part is basically fixed and also may be seen and imported by maybe some other dynamic part, like a machine, right? So you want to make sure that, understand that the fixed part, anything that should be fixed and stay constant should be declared in the static part, like a constant values. And we're only going to have one single constant value called D over here. And D is going to denote the maximum number of cards allowed to be on the island bridge compound at any time, right? So it's really critical for you to understand at this point, we're using the abstraction that we already applied to our initial model. We don't have the notion of a bridge. All we have is between the mainland and also the compound of the island and bridge, right? There's no distinction between the island and the bridge. There's simply no, right? That's the abstraction that we spoke about just earlier. And this constant D, and for the case of the theorem proving, we do not need to give any particular value, like a specific value for the maximum number, like a D over here. And for theorem proving, as I said before, as a contract, like on the contrary to doing some JUnit testing, in the case of theorem proving, all we gotta do is to specify the typing constraint or any additional assumptions for the constant or variable. In that case, the theorem proving will be able to argue the property at the abstract level, at the predicate inference level, in which case, once it is proved, it's going to be universal for all the possible values for all the configurations, right? That's something we also spoke about earlier. I just want to make sure it's connected to you. Right, so that's a constant. I'm going to annotate to see how it can be applied to our abstraction visually. And you want to know that on the mainland, the number of cards is simply just unbounded. All right, and then so these will be the constant. There's only a single constant, just D over here. All right, just D. And what about it would not be sufficient for you to just declare the name of the constant. You have to specify what type it is. That's always one thing you have to make sure is associated with each constant you declare. In this case, we say that the constant is simply a member of the set of natural number over here, right? I think at this point it might be good for me to visualize a bit before I get to the dynamic part. Okay. Right, so that's again, we are only addressing requirements number 2 in this initial model, right? For now, you can simply ignore this part just for now, right? But we're going to cover this part only, okay? So we got our constant D, and you can think about D is really addressing this particular compound over here, the maximum number of cards that can be existing over here. Okay, so the idea will be maximum D cards in this compound, which means it cannot be more than that, right? Up to and including D, all right? And then what about the axioms over here? Axioms are simply something that assume to be true. We don't need to prove it. It's usually to give us more information about the constant or sometimes variables. Assume to be true. And I want to talk about the naming convention for the label as well. If you look at the label over here, axiom 01 over here, right? So there are different parts over here. If you look at AXM, of course, that means axiom. And you will see THM later. It actually stands for theorem. Well, we'll definitely see that later. But theorem, it's actually THM will be for theorem. All right. And you want to see also this one as well. Let me use a different color here. And the 0 over here is really talk about initial model, model number 0. Initial model M0. You want to be able to actually tell what it really means from each label, so you know exactly where you are in the model. And whenever there's anything that cannot be proved or something you want to use for your proof, you can actually properly reference it. And finally, this one over here is simply, that means it's the first axiom, right? Of course, the next one will be AXM 0 underscore 2. That'll be the next axiom. First axiom of M0. Right? It's really important for you to see how the label should be interpreted. And all we say over here is D should be a natural number, meaning that the minimum value for D can be should be 0, and then it cannot go below 0. That makes sense because you definitely cannot have -1 cards in the compound, can you? No. All right, so that's about the static part, which usually should be encoded into the context in Rodin. Right? Let me also mention that the static part should appear as context in Rodin. All right, I believe I covered everything. Okay, let's now go back. Okay, and we're going to talk about the dynamic part as well. Right, the remark, something I said, so axioms are assumed to be true, and you definitely don't need to prove them. Well, remember also what we did in lab 1. So we saw that there was no associated proof obligations for axioms, but whenever you declare something not axiom, in that case, it will become some proof obligation for you to discharge, either automatically or manually, right? Let's talk about the second part for the model. So the second part usually is more important and trickier to understand, but for the initial model it's okay, but I'm just saying in general. The constant part, the static part should be rather straightforward, but you should really know exactly which part of the requirements it is trying to encode. In this case, requirement number 2, right? That's the only requirement we are addressing for the initial model. The dynamic part changes as the system evolves. So system evolution is also a very key term you want to understand in this course. So when we are building a reactive system, you can think about the system basically never terminates, unlike your maybe quick sort or merge sort that you did earlier. Usually, given the input of even 1 million elements, it would simply take some time, maybe up to I don't know, maybe a few minutes. If you got a very efficient algorithm, maybe only after a few seconds, it will terminate, and that's it, until you actually pass the next input. But when we talk about reactive system, it will be very important for you to actually know. Let me make a note over here. So when we talk about dynamic, right? Basically, we are talking about interactions between the system and its users. Continue. Presumably can think about it's going to continue forever. Let me say forever just for now. Which means it's not unlike any sequential or like a sequential algorithm, in which case the algorithm will terminate. But in this case, it was the bridge controller, well, maybe until the time it has to be fixed or maintained, it will always be under operation. You will be definitely in operation. It will definitely be interacting with any users, in this case, the cars. All right. A variable n, that's the second name that we're going to introduce. The first one was D, and now it's n. N denotes the actual number of cards at a given moment in the island bridge compound, right? So let me make a note right away, all right? Actually, before that, let's go over the type, first of all. You can see the variable list, we only got only one name in the list, which is variable. Now you want to know fundamentally what's the difference between constants and variable. Well, the difference is pretty much like how you understood in programming, like in Java. So constant basically fix its value always, even though in the case of specification in theorem proving, we don't need to know what value D is. But in the case of programming, you definitely you should always initialize the constant to be some specific value. Otherwise, it would be a compilation error. But in the case of specification, you can see that here we don't have to say exactly what value is. We only have to say it is simply just a member of any natural number. Okay. And for the variables over here, let's see what the invariance is. So invariance over here, so this one here is more so-called a typing constraint. We are saying that the variable n is a member of the natural number, meaning that it might be initialized to be any natural number, and as we actually try to perform updates on the variable through the execution of the events, which I'll talk about later in the later slides, you want to make sure always n should remain as a member of the natural number, right? That's something we'll see as well. I'll do some simulation on the paper together with you, and this will be more like a property over here. In this case, we want to say n should be limited up to and including d. So this is really what requirements number 2 was saying. The number of cards actually in the bridge island compound should be limited, right? Okay, let's now make some annotation over here. Right, again, you can see the label over here. You can see IMV over here, it's invariance, right? IMV over here is really just invariance, the short form for invariance. And you can definitely see also 0 over here, just the same as the 0 over here for the axiom. So it's simply the invariance for model 0, the initial model. And we got invariant number 1, invariant number 2, right? Just the numbers will simply will simply keep going, okay, as we add more invariants. And you want to understand the difference between fundamentally this one here, n is a member of natural number, right? So this one over here is more like a typing constraint. On the other hand, this one over here, let me just try to do n is less than or equal to d. So this is more like a property that we would like to establish, more like a property. Let's say for now, anything that's not to specify the type of a variable, or maybe for a constant, they should be considered as like a property that you may just want to prove, right? All right, so let's now try to visualize how n and d should be understood, right? We know that from the static part, the number of cards in this particular compound should be up to and including d, right? But at any given time, as we actually try to, if there's any card that move out from the mainland to the island and bridge, the number of cards in this particular compound should be incremented. Versus, if there's any card already in the compound, they want to move back to the mainland, in that case, the number of cards should be decremented, right? So we should really have such counter to really tell us exactly how many cards are there in the compound. So that's exactly what n is supposed to record. Okay, so in that case, I'm going to put the n over here, right? So n will be the number of cards in compound at the moment currently. And of course, the way for us to really make a connection between the constants and also the variable is we want to make sure we actually specify this particular invariance, which will be the n is less than or equal to d. So that's really the property eventually we want to satisfy. Okay, you can see this part over here is really corresponding to this part of the requirements. The number of cards, which we know is n, is limited, right? Let me just get it even more explicit for you. You really want to know how to trace from informal requirements to the formal model and vice versa. Okay, so what we did was this part over here, the number of cards, it will simply just be n. So that's the variable, and it is limited. So that means n is less than or equal to d. Okay, we just use different color over here. Less than or equal to. Right, you can see the n and also d. So these are the only two values that we actually use in the initial model to address this particular requirement. As you can see, only using these two values will be sufficient to address these requirements. There's no need to really talk about bridge and also island. For example, more specifically, we don't really need to declare any variables or constant in the initial model, and one is called bridge and one is called island. It's simply not necessary, right? That's why we said it's about abstraction. All right. You can see even for the simple model like this, there are many things you want to learn from this constructing this model, right? You want to make things as simple as possible, just not simpler, so that you will lose information. But I think this will be simple enough so that we can capture the essence for requirements number 2. All right. Let me now go back to the slides, right? And the remark will be the invariance should be subject to proofs, meaning that whatever invariance we specify for the variables in the dynamic part, they should be somehow proved to be consistent. And we'll definitely talk about the proof obligation later this week. We'll see. Right? So there are 2 things intuitively you want to really remember always. Number 1, the invariance should be established when the system is first initialized. Number 1. And also we say that invariance should be preserved. I think that's the term that's used in the textbook. But people also like to say the invariance should be maintained as well. So these 2 terms may just be used interchangeably, right? And after any enable events action take effects, right? Let me just give you some diagram over here, which I'll give you more elaborate drawing later when I speak about events and abstract state machine. What you want to understand this is, you want to think about the state space. What we're going to do is we're going to represent each configuration of your state space as a circle. Okay, so the very initial configuration you want to think about for your system is going to be, I just have an arrow over here. I know that for you guys, actually from the software engineering major, you didn't really take the EECS 2001, which is about introduction to the theory of computation. So you wouldn't have learned about like a finite automata, but that's okay. I think the idea about abstract state machine, even though it's very similar to finite automata, but I'm going to give you just an example. I'm pretty sure it's quite straightforward to understand. But if you got any doubts about the basics about abstract state machine as I talk later, you can definitely reach out to me. Okay, so what we want to say is we're going to start with, so that's why there's an arrow over here, meaning that we're going to initialize the system. Okay, once we initialize the system, there's going to be certain state configuration over here. I'm going to leave out exactly the configuration, the valuation for D and also N, unspecified. We don't need to. Okay, but what's really important is we want to make sure all the invariants, let me for now, for the purpose of illustration, let me say all the invariants over here, invariant 1 and invariant 2. Okay, let me just use a capital letter I. So that means I should be, you can think about I is more like a conjunction of all the invariants. N should be a member of the natural number, and N should be less than or equal to D, right? So let me put it down. It's by definition, N should be a member of the natural number, and conjunction, N should be less than or equal to D, right? So that's the invariance you want to keep in mind. And we want to make sure this invariant over here, if you try to evaluate this particular proposition, right, it can be either true or false. For the initial configuration, this particular configuration should really evaluate the invariance and return true. All right. So that means I over here should be true, right? So I'm just going to use green to say it's actually true. All right. So this is what we said the invariant is established after initializing the system. That's really the first step. And analogy would be, if you want to prove things by mathematical induction, what will be the first thing to really prove? You want to prove for a small number of base cases. That's really about establish the invariance of your system, right? That's kind of analogy. And what will be the next step for your mathematical induction? You want to make sure, and whenever for every state, when you go from one state to another, we'll go from I to I plus 1. The theorem you want to prove can also be demonstrated, right? That's kind of this recursive case for the mathematical induction. And for the invariance, we call that whenever you want to make a state transition, you're actually going to preserve or maintain the invariance, right? Diagrammatically, let's say what we're going to do is we're going to maybe go from one state to another. Let's say, let me just put another state over here. This is simply just another state. And you don't need to know, So this arrow over here is so-called the state transition. Okay, let me just make some more notes over here. So this is called state transition. And for our purpose, this state transition corresponds to any events of your machine. right? Remember in your lab number 1, we actually created events for your bank machine. And we're going to create 2 events. One will correspond to when the car moves from the island into the compound. And we're going to get another event which correspond to a car that leaves the compound and go back to the mainland. These are the 2 possible transitions we might make. But for now, let's say this transition can be any one of them. After making the transition, you want to make sure if you evaluate the invariance condition, which I define over here, it should again be true. You want to make sure if there's any transition you can make from one state to another, it should be maintained, right? So now we talk about 2 cases. So this one here is about I being established. And this is the case where you go from one state to another, you're making a state transition, the invariant is preserved or maintained. I'll just use the textbook term, but I personally prefer maintained, but that's okay. I preserved. Right, I'll give you more details later, but I think that this will be good enough for you to understand what's really the difference between establishing the invariance versus maintaining the invariance. They're both important to know. You cannot really lose anyone. Each one of them will be some individual proof obligations you will have to discharge by the Rodin theorem prover. All right, so that's about the state space, right? And hopefully you're okay so far. So we learned about exactly how the state space is like by applying the certain abstraction which we discussed. And the next step is to really see how we can make some transitions between configuration of the state space. And we're going to talk about events.